August 15, 1904, Panama Canal Zone. The engineering assessment from European excavator manufacturers would never fully capture the impossible conditions they encountered that sweltering morning. American steam shovels, operating in tropical heat that European machines couldn't survive. Through the constant downpour and suffocating humidity of the canal construction site, Marion and Bucyrus excavators moved earth with reliability that seemed impossible to European observers. No planned replacement schedules, no regular factory rebuilds, no acceptance that tropical conditions meant inevitable failure. Yet they dug continuously while European machines broke down weekly. In European factories, engineers designed excavators expecting 18-month service intervals and component replacement every 6 months. Each machine required constant maintenance cycles that made tropical construction projects nearly impossible to complete profitably. Most carried operating costs that doubled every year of service. The Americans were building with engineering philosophy the Europeans had dismissed as primitive fantasy. Steam power over hydraulics, bronze bearings over complex mechanisms, steel construction designed to last decades, not seasons. Manufacturing standards that prioritize permanent operation over planned obsolescence. 7,000 miles from European drawing boards, the most decisive excavation revolution in construction history was proving itself, not through sophisticated complexity, not through premium engineering, but through the systematic durability that connected every American component in ways European planned obsolescence never imagined possible. 22-year-old William Otis stood at the edge of the Canton, Massachusetts Railroad, cut in the bitter February cold of 1835, watching 400 men attack 12,000 cubic yards of granite and clay with hand shovels and pickaxes. The European-trained engineers who had designed this section of the Boston and Worcester Railroad calculated that moving this much earth would require 2 full months of backbreaking labor. Steam locomotives were revolutionizing transportation, but excavation work remained exactly as it had been since Roman times. Men with tools, muscle against stone. The mathematics were brutal and simple. Each laborer could move roughly 30 cubic yards per day under ideal conditions. Winter in New England provided no ideal conditions. Frozen ground required pickaxes to break every shovelful. Wheelbarrows became useless when their wooden wheels cracked in sub-zero temperatures. The daily wage of $1.50 barely covered food and lodging for workers who destroyed their bodies, moving earth that machines should handle. Otis had spent the previous 3 months studying every aspect of excavation work, timing how long it took to fill a wheelbarrow, measuring the distance workers walked between dig sites and dump, areas calculating the energy wasted in repetitive motions that accomplished nothing productive. His engineering notebooks filled with sketches of mechanical solutions, steam-powered winches, rotating buckets, articulated booms that could reach into excavation sites without requiring workers to climb down dangerous slopes. The breakthrough concept emerged during a December evening in his Philadelphia workshop. Steam engines were already proving their superiority over human muscle in factories and transportation. Why not excavation? The technical challenges seemed manageable. A vertical boiler could generate sufficient pressure to operate a hoisting system. A rotating boom could position a digging bucket anywhere within a 30-foot radius, and a toothed bucket could break frozen ground more efficiently than any pickaxe. Working through the winter months with engineer Charles French, Otis constructed his first steam-powered excavator in a converted blacksmith shop. The machine featured a crude but functional vertical boiler mounted on a wooden platform, a fixed mass supporting a swinging boom, and a 1 cubic yard bucket equipped with forged steel teeth, capable of breaking through frozen clay and loose rock. The revolutionary element was the cable and pulley system operated entirely by steam power, no human muscle required for any excavation function. Initial field tests exceeded every expectation. The steam shovel moved 300 cubic yards of earth in a single 10-hour day, accomplishing the work of 25 men while consuming only coal, water, and basic maintenance. Railroad investors who had watched skeptically during construction suddenly recognized the transformative potential of mechanical excavation. Orders arrived from railroad projects across New England. But success created unexpected problems. The primitive steam engine, built with available materials and limited manufacturing precision, suffered frequent breakdowns under the constant stress of excavation work. Boiler tubes leaked when operating pressures fluctuated. Cable drums wore unevenly, causing dangerous load shifts that threatened to overturn the entire machine. The wooden platform frame, adequate for stationary operation, cracked under the dynamic stresses of boom rotation and heavy lifting. More seriously, funding became critically tight as winter extended construction schedules beyond projected completion dates. Railroad companies had allocated specific budgets based on European engineering estimates for manual excavation. The steam shovel reduced labor costs dramatically, but required ongoing investment in coal, replacement parts, and skilled operators who commanded higher wages than common laborers. The harshest lesson came during a March blizzard that shut down operations for 8 consecutive days. European-trained project managers argued that weather delays proved mechanical excavation was less reliable than manual labor, which could resume immediately when conditions improved. Steam shovels required dry coal, unfrozen water supplies, and mechanical adjustments that couldn't be performed in severe weather. By late March, several railroad investors threatened to cancel their orders and return to manual excavation methods. The steam shovel had demonstrated its potential, but reliability problems and weather sensitivity created operational risks that conservative project managers refused to accept. European engineering practices emphasized proven techniques over innovative approaches, regardless of their efficiency advantages. Otis spent sleepless nights in his workshop, studying every component failure and analyzing why European steam technology, designed for factory applications, couldn't handle the punishing demands of excavation work. Factory engines operated in controlled environments with predictable loads and regular maintenance schedules. Excavation required machines that could function reliably in extreme weather, handle shock loads from hitting buried rocks, and operate continuously for months between major service intervals. The realization that conventional steam technology wasn't sufficient for excavation work forced Otis to confront a fundamental engineering challenge. He needed to develop not just a steam-powered excavator, but an entirely new category of machinery built specifically for decades of daily punishment in harsh outdoor conditions. European manufacturers had never faced this requirement because they accepted that complex machinery required frequent servicing and replacement. Standing in his workshop on a cold April evening, examining the worn components of his prototype excavator, Otis understood that his vision demanded engineering philosophy fundamentally different from European practices. He wasn't just building a machine to move dirt faster. He was creating proof that American engineering could build equipment designed to outlast its builders. The question was whether he could develop the manufacturing techniques and material science necessary to make that vision reality before skeptical investors lost faith entirely. Returning to Philadelphia after the Canton project's mixed results, William Otis spent the summer of 1836 developing what would become his revolutionary design philosophy: build it once, build it forever. The concept emerged from careful analysis of every component failure experienced during the New England winter. Conventional manufacturing accepted that machinery would wear out and require replacement. Otis rejected this assumption entirely. His excavators would be engineered for indefinite service life through superior materials, redundant design, and field-repairable construction. The breakthrough came during metallurgical experiments in his expanded workshop. Otis discovered that steel cable, properly manufactured with consistent wire tension and protective coatings, could lift 3,000 pounds reliably, while conventional iron chains failed catastrophically at 800 pounds. This wasn't simply a matter of material strength. Steel cable distributed stress across hundreds of individual wires, so damage to any single wire wouldn't cause total failure. Chain links, by contrast, concentrated all stress at their weakest point, guaranteeing eventual catastrophic failure under repeated loading. Working through the winter months of 1837 and 1838, Otis developed 3 fundamental innovations that would transform excavation engineering. The powered boom swing eliminated the dangerous manual rope pulling that had injured operators during the Canton project. Steam cylinders provided precise rotational control, allowing operators to position buckets with surgical accuracy while maintaining safe distance from excavation edges. The chain-operated dipper crowd mechanism gave operators mechanical advantage ratios of 8-to-1, enabling fine control over digging depth and bucket angle that manual systems couldn't achieve. Most crucially, Otis engineered every component for permanent installation rather than periodic replacement. The steam boiler used 1-inch wrought iron plates riveted with overlapping seams that distributed stress across multiple connection points. Traditional boiler construction relied on single-thickness plates with butt joints that concentrated stress and failed predictably. Otis's redundant seam design meant that even if individual rivets failed, adjacent connections would maintain pressure integrity. The boom assembly employed solid forged steel pins that could be turned and remachined countless times as bearing surfaces wore. European excavator manufacturers used cast iron pins that required complete replacement when wear exceeded tolerance limits. Otis's pins were machined oversize initially, allowing operators to remove material and restore precise fits through decades of service. Cable drums featured replaceable bronze bushings rather than integral bearing surfaces, transforming major repairs into simple maintenance procedures that field mechanics could perform. Typhoid fever claimed Otis's life in September 1839, just months after he filed his comprehensive patent application covering all three revolutionary innovations. His widow Elizabeth faced immediate pressure from investors and competitors to sell the patents or license the technology to established manufacturers. Instead, she committed to continuing her husband's work, spending months studying his technical drawings and manufacturing notes to understand every aspect of excavator construction. Elizabeth's decision to marry contractor Oliver Chapman in 1844 created the perfect partnership to advance Otis's engineering vision. Chapman brought practical construction experience and mechanical intuition that complemented the theoretical innovations documented in Otis's patents. More importantly, Chapman shared Otis's fundamental belief that superior engineering meant building equipment that outlasted its builders. Chapman's first major contribution was refining the chain crowd mechanism to achieve the precise bucket control that made Otis excavators superior to European designs. Traditional excavators relied on operators manually positioning buckets through rope and pulley systems that provided limited control over digging angle and penetration depth. Chapman's chain-operated system used mechanical linkages that maintained consistent bucket orientation regardless of boom position, enabling operators to dig clean, precise cuts through varied soil conditions. The engineering challenge was translating operator input into reliable mechanical motion through a system that could function flawlessly across decades of daily operation. Chapman developed a chain and sprocket arrangement that provided 8-to-1 mechanical advantage while maintaining positive engagement under all load conditions. The chain links were individually replaceable, the sprockets were machined from tool steel that improved with wear, and the entire mechanism could be disassembled and rebuilt in the field using standard tools. By 1850, when railroad construction accelerated across the expanding American frontier, Chapman's company had established manufacturing processes that ensured consistent quality across all excavator production. Each machine underwent comprehensive testing that simulated years of operational stress. Boilers were pressure tested to twice their intended working pressure. Cable systems were loaded to 150% of rated capacity and cycled through thousands of lifting operations. Boom assemblies were subjected to side loads that exceeded anything encountered during normal excavation work. The results validated Otis's original vision spectacularly. Chapman excavators consistently operated for decades with minimal maintenance beyond coal, water, and occasional cable replacement. Railroad contractors who had initially viewed mechanical excavation as an experimental curiosity now demanded Chapman machines for every major project. The superior reliability and precise control capabilities made manual excavation economically obsolete for large-scale construction. When the Otis patents expired in 1870, Chapman's company had manufactured 67 steam shovels. Every single machine remained operational after 3 decades of continuous service, many still performing their original excavation work on railroad projects across the growing American frontier. European manufacturers had produced hundreds of excavators during the same period, but their planned obsolescence philosophy meant that most required major rebuilds or complete replacement within 10 years. Chapman's achievement wasn't simply building better excavators. He had proven that American engineering philosophy could create machinery designed to outlast the men who built it. The contrast with European approaches was stark and decisive. Where European manufacturers maximized profits through planned component failure and regular equipment replacement, American engineers maximized value through permanent construction and indefinite service life. Edward Huber arrived in Marion, Ohio in 1884 with manufacturing experience from Cincinnati's machine tool industry and a radical conviction that American excavator engineering had barely scratched its potential. While established manufacturers celebrated the expiration of Otis patents as opportunities to produce cheaper imitations, Huber founded the Marion Steam Shovel Company with the opposite philosophy: engineering for the long haul. His goal wasn't building more excavators, it was building excavators that would never need replacement. Huber's first step was systematic analysis of every excavator failure reported across American construction projects. He dispatched engineers to railroad sites, mining operations, and canal projects to document exactly how and why steam shovels broke down. The data revealed patterns that conventional manufacturers had ignored. Boom assemblies failed not from normal excavation loads, but from dynamic stresses created when buckets struck unexpected obstructions. Boiler tubes cracked not from operating pressure, but from thermal expansion cycles during startup and shutdown. Cable systems wore out not from lifting weight, but from improper drum alignment that concentrated stress on individual wire strands. Most significantly, Huber discovered that excavator failures followed predictable patterns based on inadequate safety factors in critical components. Industry practice used safety factors of 2 to 1. Components were designed to handle twice their expected working loads. Huber calculated that excavation work imposed shock loads and stress concentrations that could exceed normal working loads by 400% during routine operation. His Marion excavators would use safety factors of 4 to 1 as minimum design standards. The Marion Foundry became an experimental laboratory for metallurgical innovation focused entirely on permanent construction. Huber's engineers developed cast steel boom assemblies using techniques borrowed from railroad locomotive manufacturing. Traditional excavator booms used fabricated construction, multiple pieces welded or bolted together into composite structures that concentrated stress at connection points. Marion booms were cast as single integrated pieces from tool steel alloys, eliminating stress concentrations while providing consistent material properties throughout the entire structure. The bronze bearing revolution emerged from Huber's observation that European excavators failed because they fought natural wear processes instead of accommodating them. Conventional bearings used hardened steel surfaces that maintained precise tolerances when new, but wore rapidly under the chiazza, contaminated conditions typical of excavation sites. Marion bearings used bronze alloys that actually improved with age as wearing surfaces developed perfect conformity with their mating components. Bronze bearings that operated roughly when new became progressively smoother and more efficient through years of service. Modular design principles transform maintenance from specialized factory procedures into routine field operations that any competent mechanic could perform. Marion excavators featured standardized bolt patterns, interchangeable components, and complete accessibility to all wearing parts without major disassembly. Boom pins could be removed and replaced using portable lifting equipment. Boiler tubes could be cleaned and inspected through removable access panels. Cable drums could be lifted out for bearing service or complete replacement using the excavator's own boom and hoist mechanisms. The standardization breakthrough came when Huber realized that part interchangeability across all Marion models would multiply the durability advantages of superior individual components. Every Marion excavator used identical cable systems, bearing designs, and control mechanisms regardless of size or intended application. Contractors could maintain fleets of different Marion machines using common spare parts inventories. More importantly, successful design improvements developed for one model could be immediately applied to all production without retooling or redesigning individual machine variants. The Great Northern Railway project provided the ultimate test of Marion's engineering philosophy against European competition. Construction crews working in Montana's brutal winters faced conditions that destroyed conventional excavators within months of delivery. Temperatures reached 40 degrees below zero for weeks at a time. European hydraulic systems froze solid, cracking cylinders and destroying seals. Cast iron components became brittle and shattered under shock loads. Complex control mechanisms jammed with ice and couldn't be operated until spring temperatures returned. Marion steam shovels continued excavating through the entire Montana winter without significant problems. Steam systems generated their own heat, preventing component freezing. Simple mechanical controls functioned reliably regardless of ambient temperature. Robust steel construction absorbed shock loads that destroyed European machines. Most impressively, Marion excavators maintained their precise control capabilities even under extreme conditions, enabling contractors to continue productive work when European equipment sat idle. The Model 91 represented the culmination of Marion's permanent construction philosophy. Introduced in 1900, this 75-ton giant could move 500 cubic yards daily while maintaining the reliability and field serviceability that defined Marion engineering. The track-mounted design used solid steel wheels 4 feet in diameter, each machined from single steel billets using techniques developed for railroad locomotive drivers. The wheels were designed for 100,000 miles of service, equivalent to decades of normal excavation work. Every component of the Model 91 demonstrated Huber's commitment to permanent construction. The boom assembly weighed 12 tons and featured machined pivot points that could be reground and refitted multiple times as bearing surfaces wore. The bucket crowd mechanism used case-hardened steel gears cut with precision that improved operational smoothness over years of service. The steam boiler incorporated removable tube sheets that allowed complete tube replacement in the field without returning the machine to Marion's factory. By 1900, Marion had established American excavator supremacy through systematic engineering excellence rather than marketing innovation. Railroad contractors specifically requested Marion machines because their superior reliability reduced project costs and eliminated schedule delays caused by equipment failures. Mining companies calculated that Marion excavators produced more total yardage over their service lives than multiple European machines despite higher initial purchase prices. The transformation was complete when European manufacturers began copying Marion design features in desperate attempts to compete with American reliability standards. However, they couldn't replicate the manufacturing philosophy that made Marion excavators superior. European companies remained committed to planned obsolescence as profitable business strategy, while Marion continued building machines designed to outlast their builders. Colonel George Washington Goethals assumed command of the Panama Canal Project in 1907, facing the wreckage of French engineering failure and a congressional mandate to complete the canal within 7 years. The tropical conditions that had destroyed French equipment remained unchanged: 95-degree heat, 90% humidity, and torrential rainfall that could dump 6 inches in a single afternoon. Goethals understood that excavator reliability would determine whether American efforts succeeded where European engineering had failed catastrophically. European manufacturers submitted bids for steam shovels designed around planned service intervals that acknowledged tropical conditions made long-term durability impossible. Their proposals included mandatory factory rebuilds every 18 months, complete component replacement every 6 months, and maintenance contracts that cost more than the original equipment purchases. The European philosophy accepted that complex machinery couldn't survive tropical punishment and built profitable service relationships around inevitable failures. Goethals rejected European assumptions entirely. The canal project required machines that could operate continuously in conditions that no previous construction project had faced successfully: 24 hours daily, 365 days yearly, for 10 consecutive years. No scheduled maintenance shutdowns, no factory rebuilds, no acceptance that tropical conditions justified equipment failures that would halt the entire project. American manufacturers responded with engineering approaches that European companies had never attempted. Marion and Bucyrus engineers traveled to Panama during 1908 to study actual operating conditions rather than relying on theoretical calculations about tropical equipment performance. They discovered that conventional wisdom about tropical engineering was fundamentally wrong. Complexity and sophistication increased failure rates rather than improving performance. The American solution was radical simplification combined with materials engineering that eliminated failure modes entirely. Self-lubricating bronze bearings replaced complex oil systems that failed when contaminated with tropical moisture. The bronze alloys were formulated specifically for high temperature, high humidity operation and actually improved their performance characteristics as they aged under tropical conditions. Conventional bearings required constant attention and frequent replacement. Marion bearings were designed to operate unattended for decades. Replaceable wearing surfaces transform major repairs into routine maintenance procedures that could be performed without stopping excavation operations. Bucket teeth, cutting edges, and wear plates were designed as consumable components that field crews could replace during shift changes. The wearing surfaces used tool steel alloys that could be resharpened hundreds of times, extending their service lives far beyond anything European manufacturers had achieved. Modular steam systems represented the most significant innovation for tropical operation. Traditional steam shovels used integrated boiler designs that required complete shutdown for cleaning and maintenance. American manufacturers developed sectional boilers with removable tube bundles that could be cleaned while the excavator continued operating on backup sections. The modular approach meant that boiler maintenance became a continuous background process rather than scheduled shutdown events. Tool steel cutting edges demonstrated American commitment to permanent construction under the most demanding conditions imaginable. The cutting edges were forged from alloys developed specifically for Panama's abrasive volcanic soil and designed to maintain sharp cutting geometry through hundreds of thousands of cubic yards of excavation. European cutting edges lasted weeks before requiring replacement. American edges operated for months between sharpenings. The results exceeded every projection when excavation operations commenced in 1909. 77 Bucyrus steam shovels excavated 240 million cubic yards over the next 10 years without a single catastrophic failure. Daily maintenance costs averaged $12 per machine, mostly coal, water, and occasional cable replacement. European manufacturers had projected maintenance costs of $50 daily per machine, assuming frequent component failures and regular factory service. More impressive than the statistics was the operational philosophy that American excavators enabled. Goethals could schedule excavation work with confidence that equipment would perform reliably regardless of weather conditions or operational demands. French engineers had planned around equipment limitations. American engineers had eliminated the limitations through superior engineering. The ultimate validation came during the wettest season in recorded Panama history, when European equipment would have been completely unusable. American steam shovels continued excavating through 6 months of nearly continuous rainfall, operating in conditions that turned excavation sites into mud lakes. The machine's robust construction and simple mechanical systems functioned perfectly when sophisticated European alternatives would have been destroyed by water contamination. European manufacturers watched their tropical market disappear as American reliability standards proved achievable through engineering excellence rather than planned obsolescence. The contrast was stark and economically decisive. European excavators cost less initially, but required constant expensive maintenance that made them economically inferior to American machines, despite higher purchase prices. Then disaster struck in October 1913, when geological instability triggered the massive Culebra Cut landslide. 500,000 tons of mud and rock buried 3 Marion excavators under debris fields that extended across the entire width of the canal cut. European critics seized the opportunity to argue that American durability engineering was useless against natural disasters that could destroy any machine regardless of its construction quality. The landslide threatened to vindicate European criticism that building for permanence was economically irrational when natural forces could destroy any equipment instantly. Insurance companies prepared to write off the buried excavators as total losses. Canal administrators calculated delays and replacement costs that could threaten the entire project schedule. But the crisis also provided an unprecedented opportunity to demonstrate the fundamental difference between American and European engineering philosophy. Rather than accepting the loss and ordering replacement equipment, Marion's chief engineer Samuel Huber proposed something that European manufacturers would never attempt: recovering the buried machines and proving they could survive even catastrophic burial in tropical conditions. The recovery operation would require 6 weeks of careful excavation using undamaged Marion shovels to dig out their buried partners. Success would prove that American engineering could build machines capable of surviving disasters that would destroy European equipment. Failure would validate European arguments that complexity and planned obsolescence represented more realistic approaches to equipment design than American permanence engineering. Goethals approved the recovery operation, recognizing that the outcome would determine whether American engineering principles could withstand their ultimate test in the most demanding construction environment ever attempted. The excavation recovery operation began on October 21, 1913, with Samuel Huber directing 8 undamaged Marion shovels in the most precise digging operation ever attempted. The buried machines lay under debris fields that ranged from 30 to 60 feet deep, their exact positions determined only by surveyor calculations based on their last known locations before the landslide. European critics argued that 6 weeks of careful excavation would cost more than purchasing replacement equipment, making the recovery economically irrational regardless of its technical outcome. Huber's strategy relied on American excavator precision to accomplish what manual labor could never achieve safely. The buried machines were located near unstable geological formations that could trigger additional landslides if disturbed improperly. European excavators lacked the fine control necessary for such delicate work, but Marion shovels could remove individual bucket loads with surgical accuracy, gradually exposing buried equipment without disturbing surrounding debris fields. The first breakthrough came on November 3rd when excavators uncovered the boom assembly of Marion shovel number 47. The massive steel structure emerged from tropical mud completely intact, its bronze bearings still packed with protective grease despite 3 weeks underwater. European manufacturers had predicted that tropical moisture would cause immediate corrosion of any buried steel components, but the boom showed no signs of degradation beyond superficial mud staining. Recovery crews discovered that American engineering philosophy had created machines capable of surviving conditions that no designer had ever imagined. The excavator's modular construction allowed systematic disassembly underwater, with each component lifted out separately and inspected before cleaning. Bronze bearings moved freely despite weeks of submersion. Steel cables showed no corrosion despite constant moisture exposure. Cast steel components maintained their structural integrity even after being crushed under thousands of tons of debris. The most dramatic moment came when crews exposed the main boiler of the first buried excavator. European boilers used thin-walled construction that would have collapsed under the pressure of overlying debris. But Marion's redundant design philosophy had created boilers capable of withstanding loads far exceeding normal operating requirements. The 1-inch wrought iron plates and overlapping rivet seams had distributed the crushing forces across the entire boiler structure, preventing catastrophic failure. Pressure testing revealed that the buried boiler maintained complete integrity despite its ordeal. Steam pressure reached normal operating levels without leakage. All tube connections remained tight. The safety factors that Marion engineers had built into every component had proved adequate even under conditions that exceeded normal operating stresses by orders of magnitude. European manufacturers watching the recovery operation realized that their planned obsolescence philosophy could never produce equipment capable of surviving such punishment. The resurrection of Marion shovel number 47 provided definitive proof of American engineering superiority. After 6 weeks underwater in tropical mud, surrounded by crushing debris, the machine started on the first attempt when crews lit its firebox and built steam pressure. Every control responded normally. All mechanical systems functioned exactly as designed. The excavator immediately resumed normal operation, moving earth as efficiently as machines that had never been buried. European observers documented the recovery operation with growing disbelief. Their excavators required major rebuilds after months of normal tropical operation, yet American machines could survive catastrophic burial and continue working without any significant repairs. The philosophical difference between European and American engineering approaches had been demonstrated in the most dramatic way possible. The second and third excavator recoveries proceeded more rapidly as crews refined their techniques. Marion shovel number 51 emerged after 4 weeks of careful excavation, its mechanical systems completely functional despite burial under 40 feet of volcanic debris. The machine's track-mounted design had actually protected its critical components during the landslide. The solid steel wheels had acted as shields, deflecting crushing forces away from the more delicate steam and control systems. Marion's shovel number 58 presented the greatest challenge because it had been completely overturned during the landslide. Recovery crews had to excavate around the upside-down machine and construct temporary supports before attempting to right it using other excavators. European manufacturers predicted that the overturning stresses would have destroyed critical components, making the machine unrecoverable even if physically extracted. When crews finally righted the excavator and began systematic inspection, they discovered that Marion's engineering philosophy had anticipated even this extreme scenario. Every major component had been designed to handle loads from any direction, not just normal operating orientations. The boom assembly showed no structural damage despite being twisted and compressed during the overturning process. Bronze bearings had maintained their protective seals even when inverted underwater for weeks. The complete success of the recovery operation transformed international perceptions of American engineering capability. European manufacturers had built machines assuming they would require replacement after predictable service intervals. American engineers had built machines assuming they would face challenges that couldn't be predicted or avoided through normal design practices. The Panama recovery proved that American assumptions were correct. More significantly, the recovery demonstrated that American excavators represented fundamentally different engineering philosophy than European alternatives. European manufacturers designed for planned obsolescence and profitable replacement cycles. American manufacturers designed for resurrection, machines that could survive disasters and continue operating indefinitely through superior materials and redundant construction. The 3 recovered Marion excavators resumed full-time excavation work immediately after their resurrection, operating alongside machines that had never been buried. Their performance was indistinguishable from excavators that had worked continuously throughout the landslide period. European competitors couldn't explain how machines that had survived catastrophic burial could function as well as new equipment fresh from the factory. By December 1913, when the last recovered excavator returned to active service, the fundamental superiority of American engineering philosophy had been proven beyond dispute. European planned obsolescence might produce higher short-term profits for manufacturers, but American permanent construction created superior value for equipment users. The Panama recovery operation had demonstrated that building machines right the first time cost less than building them wrong repeatedly, even when natural disasters tested equipment beyond any reasonable design requirements.